Well, guess what, kids? We made it to our last lesson. That's right, it's the last lesson of the year. Yeah. Yeah, you can get a little excited. All right. Now, hopefully, you'll be equally excited about the topic itself, which will be the application of logs. Now, in all seriousness, I like this lesson, and I hope that you do too, because it probably represents some of the more realistic applications and situations that we can look at all year. That's because most of them are going to be dealing with some type of exponential change, that is, some type of percent change, and a lot of things in the real world change in that manner. Now, if you look at the top of your paper here, you see quite a list of formulas. I hope many of them look familiar, but maybe your eyes catch some of the ones that are a little newer, like the second to last one here. It turns out that this is the natural growth model. It is the natural growth model. We'll take a look at how to use that in a moment. And in this last one here, well, it might be the one that ends up being the most interesting, as you're going to discover that it models in a very realistic way the growth or the spread of a virus. Honestly, the coronavirus, we'll find out, is modeled and can be modeled using this type of formula. You'll have to stay tuned to see that in our last example. So let's look at example A. It looks like what we have here is the rate of inflation. It looks like that it's 3.5%. It's actually a little high. I looked it up more recently. It's been a little lower than that, but it's a percentage, so it makes for a good exponential problem. We've got somebody telling us that the school lunch costs $1.85, but some time ago it was only $1.35. How long ago was that? Now, we want to use one of the formulas to get this answer. We don't want to try to use brute force. This is a good example of just a basic exponential percent change. So we're going to use the exponential model, which means that all we really need to have is a final value. $1.85 would be the final value. Maybe it's more easy to see that $1.35 would be the initial value. Now, we do know what the rate is, and since it's inflation, it's going up, so we use a plus sign, and what we're solving for here is the variable. So, nice classic example. Find the exponent, solve for t, do the stuff that we've been doing with our equations. I hope that you would divide by 135. When you divide by 135, you do get about 1.37. I always tell the students, just leave that number on your calculator, because what's coming up next is you're going to slap both sides with a log. And so when you do the log of both sides, you already have that number on your calculator. You can do the log of that entire decimal, and you can divide it by the log of this 1035 number. So try to be as accurate as possible. This is when you get your calculator out to get your final answer, and you're going to end up with right around 9.16 years. It is in years because your rate was in years, so the time is always going to match the rate. Let's move over here to example B. It looks like what we have here is radium, which was used for cancer treatment and in paint. It decomposes radioactively, and its half-life is 1,800 years. Now, we're going to use this example to help explain the idea of continuous change. That is, anything that occurs in nature can fit into this formula n, or y equals n e to the kt. Now, did you notice that this formula is really just the PERT formula with a slight modification to be a little more generic? In other words, for any type of continuous change. Now, things that occur in nature will change continually. And when we dig a little deeper into this formula, we find out that the first thing we need to do is we need to find k. Now, students sometimes ask, well, what is k? And remember, k is just a constant. And it turns out that all we really need to be able to find k is a final value, an initial value, and a time. And believe it or not, all that information is wrapped up in this small sentence that the half-life is 1,800 years. How exactly? Well, if the half-life is 1,800 years, that means that whatever I start with, I'm always going to end up with half of it after 1,800 years. So 100%, I can plug in 1,800 for my time. Now all I need is an initial value and a final value. And the reality is that I could pick any initial value, maybe like 1 gram, which means that I would end up with a half a gram after that 1,800 years. You say, Mr. Naylor, no, that's not what I was going to use. I was going to use 10. Well, if you wanted to use 10, that's fine. That means that you would have ended up with 5 grams after 1,800 years. But look what's going to happen after you start the problem. That's right, you're going to divide by 10, and you're going to end up with a half. So either way you shake it, this problem is destined to require us to do the ln of a half. And so I'm going to solve for k. We're going to do the ln of a half like we've always done, or we're going to do the ln of both sides like we've always done. And, of course, we'll have to finish by dividing by 1,800. Now, you can do all those steps on your calculator. If you take a careful look here, you see that I can take the ln of a half and divide by 1,800, and I kind of get this strange number. Now, it's just a scientific number, and honestly, I like to change that to a decimal in this problem just to help students understand that k is really just equal to a number, and it's a small number, and it's a small negative number, but if you move the decimal place 4 places to the left, we can make a good argument here to have negative 0.000385 for k. Now, once I have k, what you want to understand is that's going to be the value of k for the rest of this problem. And so if I want to actually answer the question, that is how much will be left after 100 years, then I'm going to be able to use my k value along with these new numbers to be able to determine that. And I hope that you would find yourself plugging in 10 for your initial value. I hope that you would use the k value that we already found. And, of course, now we have 100 years that we can actually plug in. Do you see here that it's clearly a two-step problem? And the first step was to find k so that we could use it to answer this question with 100 years. And just take a look at how I plugged this one into the calculator. No reason I can't kind of plug and chug that. But I don't need to use ln's. I just need to use the E button and carefully raise it to that power to get our 962 answer. Now, 962 shouldn't come as a big surprise to you because it's only 100 years, and in 100 years you're not going to decay that much of the radioactive material, especially because it takes 1,800 years for half of the material to disappear. As we slide down here to example C, we see a situation that involves an earthquake being modeled by a logarithm. In fact, the Richter scale number is a logarithmic formula. Now, look a little more closely at this formula. We've got some parts of it. We've got A. A is the amplitude. We've got T. T is the period. And then we've got this B value. It says that it's a factor accounting for weakening. It turns out that what it really does is shifts your value vertically. So we end up with a positive Richter scale number. So new formula, but can we make sense of it? I think we can. First of all, it looks like 6.4 is that Richter scale number. We can actually plug that in for R. It looks like that we've got this amplitude value, amplitude of 300. Remember that amplitude is just the distance from the midline of a graph to a max or min. And then we've got this 4.2 number, which again essentially is like a shift. It's just adding to your logarithm. So what are we trying to find? Well, of course, we're trying to find the period. We're trying to find the distance from point to point. But look at where the period is. It's in the denominator, and to make matters worse, it's kind of wrapped up in this log. So we're going to have to get our best algebra skills to work here. We're going to have to solve this thing for t. but you know how to do this. You know that you're going to work from the outside to the inside. I would assume that you're going to subtract 4.2 first. Now, you get 2.2 equals the log of 300 over t. And so now comes the time where it's time to get rid of the log. Now, don't get rid of a log by using a log, but do get rid of a log by doing a base. And remember, the base in this problem has to assume to be a base 10. It's a common log since it's not shown. So we can base both sides with a 10. Now, when you base both sides with a 10, it cancels a log, but it creates an exponent over here. It creates 10 to the 2.2 power. It's kind of like 10 squared and some, and that's why I end up with greater than 158. Now, this number, as I've said a couple times, leave it on your calculator so that you can finish solving this for t. And maybe you'll find yourself cross-multiplying. Maybe you'll find yourself doing some dividing. In the end, it does come out to be 300 divided by 158, which gives us a period of 1.89 seconds. So we can do problems that involve new equations. We can do problems that involve continuous change type of equations. And we can do problems that involve just a basic percent equation. But I want to look at one more problem that, as you're going to discover, is able to fit into the natural continuous change formula. Because students will often ask, well, how do I know if I'm supposed to use the natural continuous change formula, this y equals ne to the kt? And the answer is simple. As long as the problem is in a continual state of change, then we can use this formula. And so here we have a sewage system. It looks like it can support 250,000 residents. And then we get some really important information in this next sentence where we have 175,000 up from 106,000 10 years ago. Once again, I want you to see that that sentence gives you enough information to find k. And the reason it's enough information is because as long as you have a starting value, a final value, and an amount of time, that's going to allow you to find the k value that goes with it. So we would have to argue that 175,000 is the final value that matches with a starting value of 106,000 over a period of 10 years. Again, another classic example of being able to solve for the exponent. I would assume that this is becoming second nature now. I hope that you're going to divide both sides by 106,000. I hope that you're going to slap both sides with an ln, and you're going to finish by dividing both sides by 10. Those are all good steps for you to do on your calculator. I encourage you to try that and make sure that you're comfortable getting a k value of 0.05013. Now, once you have that k value, you're able to use that to come up with basically your solution. In this case, as it's worded, when is the system going to need updated? And I want you to see here that we also have the ability to be able to rearrange the starting and final values. That is, this time we're going to use 250,000 as our final value, but that means 175,000 has to be your initial value. We can change 175,000 to be our initial value since it's now at a different period of time. And of course, we're looking for the new amount of time that's going to be required to do that. And it looks like we have ourselves the same type of algebra. Again, divide both sides by 175,000, do the ln of both sides, and don't forget to finish by dividing by your k value. So here we'll know that the system's going to need updated in 7 years. Now, of course, that's 7 years from our new starting point, 7 years from 175,000. The other reason I want to do this problem is because I know that there's students that will ask, but Ms. Naylor, couldn't I have done this problem using the basic exponential model? Couldn't I have done this problem basically thinking about this as just percent change? And honestly, the answer is yes. Now, if you would do this problem using the percent change model, you would not get the exact same 7-year answer, at least to the decimal place, but it honestly comes out very close. And so the simple answer is, if you decided to do this problem with the exponential model, you would still get full credit. You would still get full credit. You just want to understand that you would have been finding the actual percent change per year versus more of a continuous change. Now, our last example you may find to be most intriguing. Not only is it new, but it also relates to something that we've all experienced over the past couple months. I'm going to be looking at logistic growth models using the book on page 222. I do encourage you to get a book if you don't have it right now, because not only are we going to do a little reading, but we're going to look at a diagram and even use the example that's on that page. All right, so do you have your book? Well, what is a logistic growth model? As you may notice from the reading, it's populations that initially have rapid growth followed by a declining rate of growth. Now, that type of change is modeled with our last formula. Our last formula is the logistic growth formula, and that can also be called sigmoidal growth. But the important thing here is to understand this is a special kind of growth where we see this increase followed by a decrease, which can be shown through this very common graph. In fact, this is always what the graph looks like for logistic growth, where we have this section of time where there is this increasing rate of growth, followed by a period of time where we want to be careful how we say this, where there is this decreasing rate of growth. Now, the reason we want to be careful the way we say this is because the graph is still going up, but it's slowing down. The rate is decreasing. And eventually, to a point where we discover that it's going to increase no more. Now, what ends up happening here is we actually have a horizontal asymptote that is often called the limiting value of your population. Now, this limiting value, it turns out, is going to be the numerator of your formula. Yes, the numerator is going to be that horizontal asymptote. And that's a really important value because that's going to be the value that we know the graph will never be able to reach, and even more particularly, ever be able to get any higher than. So, does this look like the coronavirus? Well, it is. In fact, all viruses spread based on this kind of model, where we see in the beginning of the time period, where we have this rapid increase. In fact, it increases greater and greater to a point where eventually it continues to increase, but we see that the increase is slowing down. We see that it's not increasing as quickly. Now you say, Mr. Naylor, that's not quite the graph that I've been seeing in the news. I've been seeing a graph where they keep talking about this leveling off. Well, here's the thing. The graph that they're referring to is the same virus, but it's describing something different. It's describing the number of new cases. And so this graph, again, describing the new cases, we find also has this important point where we're going to see a slowdown effect. You see, in the beginning, the new cases are obviously going up, and in the end, the new cases are going down, but we want to understand that we still are increasing. We're still growing with our total number of cases. And that's what the graph initially that I showed you here demonstrates. This is the total cases, which again keep going up, but they keep going up in a different way until a point where they start to level off. And we can see that our new case graph also levels off. It levels off to a different number. It, of course, levels off to 0. So, in summary, both of these graphs are describing the spread of a virus. One of them is describing the total cases, which do keep going up, but of course they slow down. And the other graph is describing the new cases, which new cases eventually uh, uh, get past this high point. In other words, this point that your leaders have been talking about, where it levels off and starts to go back down. So both of them relate to our model. Both of them relate to our formula. And I'd like to actually use example A to look at this a little more closely. Now, we won't recopy everything out of the book. Excuse me, it's not example A, it's example 5. But look in the book, because what we have here is a college campus of 5,000 students where somebody returns with the flu. Now, question A is asking for the number of students infected after 5 days. All right, so for our last example, we're going to be taking a look at what's known as logistic growth. Now, I think you'll find this to be rather intriguing. Not only is it new, but it also relates directly to something we've all been experiencing over the past few months. I'm going to be using the book, so if you don't have a book, I encourage you to push pause and go get it. Open up to page 222. There'll be a little reading. There's a diagram, and we even will use the example that follows to help understand this last concept. So, did you see what is logistic growth? Well, it's for populations that initially have rapid growth followed by a declining rate of growth. We'll look at that a little more closely, but I want you to realize that that is this last formula that you saw. You may want to label it as logistic growth. Logistic growth can also be called sigmoidal growth. What's most important, though, is that you understand what type of change this is describing. Let's look at the diagram that was provided, and maybe you want to resketch it. I want you to know that this diagram, this graph, is actually always the shape of logistic growth. What we see in this type of growth pattern is this beginning stage of what we call increasing growth. Now, when we have an increasing rate, let me get that word rate in there, we have this increasing rate of growth. It will then be followed by a period of time where we have this decreasing rate of growth. Now, we want to be careful here that we truly understand what it is that's being said. I am not saying that the graph is decreasing. I am saying that it has a decreasing rate of growth. Because the interesting thing here is that it is definitely true that this graph is going up all the time. It's just about the way that it's going up. You see, in this beginning section, it's going up rather rapidly. It keeps getting steeper. In this second half section, we see that the graph continues to go up, but the way that it's going up is slowing down. That's because there's a decreasing rate. In fact, it's slowing down to the point where it's eventually approaching what we call a limiting value. Now, the limiting value is actually a horizontal asymptote. And of course, that would be a line or a value that we're never going to reach or go over. And it turns out that that's actually the numerator of your formula. Now, this is actually exactly the same way that the coronavirus has grown, has changed, in that it has had a period where there's been this rapid increase that we saw in March and to mid-April, until we got to a point where it continued to increase, but the way it was increasing was slowing down. Now you say, but Ms. Narrow, that's not the graph that I've been seeing in the news or that my leaders have been talking about. Well, you see, they're talking about a graph that is representing a different facet of the spread of the virus. They're talking about a graph that describes the total number of new cases, where the total number of new cases eventually reached a maximum. And after that, we still had new cases, but that total number of new cases started to go down. And so this graph that actually looks like the bell curve, again, is describing the new cases, where one day the total number of new cases reached its maximum. Now, I still had new cases, but those new cases each day became less and less until eventually we reach a different limiting value, and that of course is the limiting value of 0 that we all anticipate when there will be no more new cases. So each graph is describing a different idea, and maybe I should describe here that this logistic graph is describing the total number of cases, where we see the total number of cases, again, keeps going up until it reaches a limiting value when we also will have no more new cases. So let's take a look at how this can work in a specific situation. I'd like to use example 5, the situation where we have a college campus that ultimately gets infected by the flu. Now, we're not going to recopy every part of it, but I do want you to see the formula, how we have 5,000 students on the campus, and it's modeled with the remaining specific numbers that you can see in the denominator. But just notice, again, the numerator is that limiting factor. There's no way we're going to have more than 5,000 students infected, so it makes sense to see that value. We also have the number 1. It's always the number 1 in the denominator along with the letter E. Now, specifically for example A, we want to find out how many students are infected after 5 days. So we have a nice little simple plug-in and chug it out. You do want to make sure that you can get your calculator to do this. I encourage you to try to pop this in your calculator and get the answer that they gave once you plug in 5 and come up pretty close to 54 students. Just be sensitive to the denominator. Make sure that you have an extra set of parentheses to compute that. How about question B? How much time until we have to close the campus? That is until 40% of the students are infected. Now you'd have to, of course, find 40% of the students. That comes out to be 2,000 students. And we find ourselves staring at a situation where we have to solve for t. Now notice where t is. Notice that it is in the exponent. So if you follow what they did in the book, you can see that they did multiply both sides by the denominator, but they also then decided to divide both sides by 2,000, which pretty quickly gets us to the point where you're looking at this denominator, 1 plus 4,999, e to the negative e8t power, that's going to equal 1.5. 1.5, again, came from dividing both sides by 2,000. And then we're at a pretty familiar place, right? You know that you're going to subtract 1. You know that you're going to divide this 4,999 number, and eventually we end up using an ln. And that'll get you your t value, which you can see that they gave a pretty close approximation there to be right around 10 days. Now, that's the algebra method. I'd like to make sure that you also can negotiate this formula graphically, which is a little more challenging anytime we get the calculator out. First off, typing the equation into the calculator, I'd like you to see here that it, again, does require careful use of the parentheses, particularly that extra set of parentheses in the denominator. Next, if we're going to graph this equation to do anything with it, we need to think about the window. Now, I know students often are challenged by a window, but what you want to keep in mind here is that we're in days. Now, I kind of made a guess here that 30 days may be all I need to see because, geez, in just 5 and 10 days, we already have close to half of the population infected. So we're going to go 30 days. And then the 6,000 number that you see here, well, I always like to go a little bit higher than the maximum amount that I know is going to be shown in this problem. And again, that maximum amount was 5,000. Try it, because you're going to have to graph one of these for your assignment. And it's kind of interesting, the graph that you get, it really is a logistic growth graph. It's a graph that shows that the population, the students that were infected, is increasing more and more rapidly until we get to this period of time where it continues to increase, but we see that it's slowing down, in fact, to a point where it eventually reaches a limiting factor, which we know is 5,000. We know that as the numerator. So can we get some of these answers that we already found for question A? Yeah, we could find the answer to question A. We could trace to to what, 5 days. And if you trace to 5 days, you're going to end up getting a y value of about 54. Now, if we want to find the answer that goes with 2,000, that is question B, what we'd have to do is we would have to graph 2,000. Now, when we graph 2,000, we'd have to type that into the y equals screen of the calculator. But then we'd be able to use this calc menu, intersect command, to be able to find the point of intersection, which comes out pretty close to be an x value of about 10 days. Now, the real reason that I wanted to show you this graph is because of this point here in the middle. You might notice that I had it shown, but we never really talked about it. And you see that point in the middle is that point that we all anticipate. It's the point when the cases, although they keep going up, that they start to have a rate of increase that is slowing down. And so there's a decreasing rate at this point right here in the middle. And again, this is the point that your leaders have been talking about as we watch the news, as we think about the coronavirus, when we find that the number of new cases is starting to decrease. And as soon as the number of new cases is starting to decrease, then we have this other side of the curve. We get to this side of the curve where we're able to eventually approach that value of 0. I'd like to give you a little encouragement here with our last assignment. First off, the formulas, remember, this is our exponential model. It's used for percent change. But this guy is our continuous change model. And just like I used in the assignment, anything that's occurring in nature, changing in nature. Now, yes, this is a little longer than some of the other assignments that we've seen over the past couple weeks. Encourage you to do a great job with it. It is something that I'm going to be grading for correctness. You can talk to people about it. You can talk, you can network, but you never want to copy. I'd rather see you carefully set these up. I want to see you carefully solve them and understand them. Understand how percentages and exponential and logarithmic changes can all wrap together in this series of questions. You'll have one more grade after this. It'll be your tests, and that'll wrap up our year.